The other is that I posted another opportunity for just miscellaneous credits to earn, and there's a conference coming up that's free, and it's on data science. So yeah, the requirement for that one is kind of open. I just want you to kind of attend. You could attend many sessions, write small things about each one. You can attend one session and write a more elaborate thing on the one session. It's kind of hope that you can get something out of that conference if you're able to. And yeah, and then there's homework due today. So don't forget to use Piazza for questions if you have any. And so what I'm going to do, and so I did post, so in Piazza, I posted a discussion. So at the end of last class, we were looking at 4 recurrence relations and how to use Master's theorem with them. And I posted how the 4th question that we have, because that was kind of the hardest one and probably the most interesting use of Master's theorem. So I'm hoping that you will discuss how to use that there. And I think so I think we'll work through the 3rd one today together, because that's kind of the trickiest of the 3. And the other 2 you can continue on your own. You're welcome to post on Piazza if you think you have a solution and you want to double check it. Yeah, so let's look at this first thing, right? So the 3rd problem from 2 days ago, which is T of n is equal to T of n over 2 plus theta of n 2 to the n, okay? So when I look at this, I say I'm given a problem of size n. I'm able to split it in half, but it takes me 2 to the n time to split it in half and build it back together, okay? I split it in half and solve that smaller half size problem. Okay, so what I want to know is the first thing we have to do, right, is we need to figure out which case it could fall in, right? And in all 3 of them, we're checking against O or theta or omega of log base b of a plus or minus epsilon. So let's first figure out what is n to the n log base b of a. So let's figure out what is n to the log base b of a. Well, a is 1. B is 2. Okay, and then log base 2 of 1 is
0.
Yay. Okay. So then we have someone who's awake. Perfect. Okay. So then we want to say question. Okay. F of n is theta of 2 to the n, and n to the log base b of a, I'll just write it like this, b of a, is equal to n to the 0, which is 1, right? And so f of n is bigger than this, okay? So this tells me that my guess is that using case 3, okay? Because this omega is a lower bound, right? Okay. So then the second step is I need to prove that we are in case 3. Okay, and so let's see. Now, if I were to do that, I have to show that all of the conditions in this if statement are satisfied. Okay, so first, let's show that f of n is equal to omega of n to the 0 plus epsilon. Okay, which, in other words, that theta 2 to the n is omega of n to the epsilon. Does this hold? How would I show this?
What is the epsilon again?
Yeah, we need to say what epsilon is, right? So we need to say, okay, so who wants to give me an epsilon? That'll make this work then. Here, there's lots of choices.
Whatever n could be, I guess. So
you want me to say epsilon is equal to n?
no, I guess I don't know. Maybe like I guess I can't pick an exact number that I think would be right here.
How about 5? 5 is a
Sure.
good number.
Yeah, sure. I like the number 5.
5th year of life was a really fun year. It really was. We went fishing a lot.
That's how you do it.
I know. And the one thing that actually I'm still getting used to here is that people fish just to catch the fish and throw them back. So we would fish for food, right? So to me, to throw back something that you can eat is just, I just don't understand.
Oh yeah, my buds do that a lot, and I don't get it either. I'm like, I worked hard for that fish.
I know. Yeah, but I still love fishing. I used to live in New Orleans, which was awesome. We would get red drum down there, and my goal is to go tuna fishing sometime in the next 5 years. So 5 is a good number. Okay, anyway, that aside. Epsilon is equal to 5. So then we have theta of 2 to the n is omega of n to the 5th. Well, asymptotics, right? This is true. So yes, this is true. Right, because 2 to the n, recall from 200 level classes that theta of 2 to the n is bigger than, I'll write it like this, theta of f of n, or well, maybe I should use a g of n here. When g is a polynomial. Okay. Let's just do another exercise here. So what if, what if f of n is n cubed, and how do I show f of n is omega of n squared? N squared. Right, suppose those were my numbers that came out. How would I show that? oops, not n.
Shot in the dark, -1.
Okay, so if I say epsilon equals 1, then we have f of n equals n cubed. We want to compare this to n. 2 minus 1 is 2, which is certainly in the omega of n squared. Yeah, so this is awesome because this works, right?
2 minus 1 is 2?
2 minus 1 is 1. Yeah, let's go with that. Sorry. Yeah. Right. So there were choices that we could have made there, right? N equal to 2 would also work. Right? If we just need to lower bound something, right? Oh wait, hold on. This should be a plus, right? Yeah. That's what I was looking for. There's an off by 1 mistake that you can make. I will make it. I know who's paying attention if you catch them. Wait, so then 2 plus 1 is not, see, look, off by like more than 1 now. 2 plus 1 is now 3, right? Yeah. And in fact, we could have had a range of numbers, right? So the largest epsilon that this could have worked for is 1, right? So note, yeah, I'm really bad at charging this pen. Right, if I had epsilon equal to 2, n to the 2 plus 2 is n fourth, right? And so n cubed is not lower bounded by this.
So what does the epsilon in the equation stand for? Or did you just use it as a variable?
This is coming from here, right? So it's all coming from Master's theorem.
Gotcha.
So let's put this. This is a good question, though. Yeah, we're working through something there. We did an exercise. I'll just draw it above here, above Master's theorem. So kind of think about, can't exactly do this, but let's pretend that every function had an exact, we knew how to classify its running time. And then we have, this is our, we'll call it timeline of increasing complexities, right? Okay, so here we would have, say, right, and it begins with our constant time because we can't get faster than that. So maybe this is our linear. Here is theta of n log n. Here's theta of n to the 800. Here's theta of 2 to the n. Okay, so there's this timeline of increasing things. Now, suppose on this timeline, somewhere here, so I'll just draw a big arrow up, we have theta of n to the log base b of a, right? Whatever that is, right? Okay. Now, case 2 is we're in there, okay? Case 2. Case 1 is if we're upper bounded by something slightly less than that. So then this is theta of n to the log base b of a minus epsilon, right? And so case 2 is I'm exactly right here, okay? Case 1 is I'm anywhere in here. Okay, and then if I were to put another one, theta of n to the log base b of a plus epsilon, right? So it's slightly bigger than that where I'm case 2. That's lower bounding where I am for case 3. So that's saying that case 3 is here. Okay, Now you might note that here and here, small gaps. Okay, so it is possible that we could fall in these gaps where we're not, that we have asymptotics, we know it's less than this, but we can't define an epsilon. It's rare, but that's a case that you wouldn't be able to apply Master theorem. You would have to, maybe there's different versions of Master theorem too. So you might, maybe there's a different version of a, like a type of a Master theorem type thing. Or maybe there's just a different technique you need to go to figure out what your runtime is. But these epsilons are kind of these buffers, right? And it says like, yeah, I'm really lower than this, or I'm really higher than this. And they just come out from the mathematics of proving this, right? Now, in this case, where I'm in this setting of proving Master theorem, proving which case I'm in Master theorem, what I've written to the right here, so this, I'll box it, this exercise in pink. Like this is enough for me to justify. If I see f of n equal n to cubed, I know that it's in the complexity class lower bounded by n cubed, okay? Now, that would be sufficient for showing that you're in Master theorem, right? As an exercise, which you do in the lower level classes, and I'll have a couple of these in the next homework, or if you're proving using the definition of what complexity classes are, right? You need to find like yeah, right. So if I had, here's my f of n, right? Right, I need to find some n0 such that for all n0 bigger than this, that there's a constant. So I need to explain what is n0, what is the constant, if I want to use the definition of the asymptotics in order to prove that something is in a certain complexity class. Okay. So I'll just put a little note here. Note for using Master theorem, you don't need to tell me what N0 and C are, but if you were using proving asymptotics by definition, I would expect them. Okay. Oops. So then, okay, so I've kind of checked off this first thing now, right? And we've discussed a little bit around this epsilon. The second condition is if A times f of n over b is less than c of f of n. Okay. Well, let's write this down here is what I need to show. Need to show A times f of n over b is strictly less than c times f of n. Okay. Now this was from a complex, so I didn't have an exact function f of n. And the trick with Master's theorem is it doesn't matter what f of n is, what the exact function f of n is, as long as you have asymptotically correct, right? If you know what theta is. So I've given it to you using the theta, right? So we know that f of n is in theta of 2 to the n. Okay, and I'll just for now, let's just assume, well, actually, we can write this. that implies there exists an n0, call it C and a D, such that for all n greater than or equal to n0, oh, we need D prime maybe. D times 2 to the n less than or equal to f of n less than or equal to D prime times 2 to the n. Okay. And we can carry through using our D's and our D primes. Okay. And this is by definition. Of theta. Okay. So what is what I want to do is I want to show this. So I'm going to show you the scratch work first, right? So I have A times F of n over B, and I want to get to, oh, sinking. Oops. C times F of n, okay? And I'll put less than is 1. Okay, so to get here, okay, let's put in my A's and my B's. So we have A is 1, B is 2. So we have F of n over 2 is less than, okay, now what was C up here? C. For some constant C less than 1. Okay. So let's put a little note that this can be is a constant we define. Okay, so we'll figure out what C is. I'm not quite sure yet. So that we want this to be less than C times F of n. Okay. Well, I know that F of n over 2 let's see. I'm going to put these to the n over 2. C 2 to the n over 2. Okay. F of n over 2. Well, I can say that this is, I can upper bound this one. So if I make this an upper bound, I could say that this is less than or equal to D prime. Okay, I can lower bound this one. So I could put a D here. Now I need to connect these two. All right, well, let's let C, let's just say C equals D prime. Okay, and now this is my scratch work. So I need to put this together, okay? So this was scratch work. I would say that I have A is equal to F of n over B, which is equal to F of n over 2, okay? Which is less than or equal to D prime times 2 to the n by definition, right? Which is less than or equal to D prime times D 2 to the n. Okay, so, oh, here we would have to say, let C equal D prime then. Okay, so this is then equal to C times D 2 to the n, right? But this is less than or equal to C times F of n, right? as desired. And then we can put whatever your favorite end of proof thing is there for this little piece. This kind of format where I kind of look at, here's what I want to prove. And I start either going line by line, what it had, like how to get from one to the other. And then, but to actually formally prove it, I had to swoop and make that U kind of shape, right? So this is scratch work. And this is something that maybe you want to think about as you're writing proofs in the class, right? There's one way that you think through a problem, and I tried to walk through this here with you so you can kind of see me thinking through it. But when I go to write it up a little more formally, it takes a little bit different of a form, right? The way you write it up formally won't, it doesn't have that step-by-step, how did I get the answer, but it's more direct, right? It's getting me there. So and this is actually speaking to something else that kind of one of the philosophies I have in learning, is that it's not about getting the answer, right? Because if I just showed you it was in green, it's less clear about how we got there, right? But it's about getting to the answer yourself, which is why for this class, I don't post solutions because it doesn't help you to read the solution, right? If you have questions, of course, I'll answer them and I'll help you get to the solution yourself. But it's really about you working through and struggling with the problems and thinking about them themselves. And that's the point of this. So even after you hand in an assignment, I really welcome you to come to office hours, post on Piazza, try to figure out how to write, what the right answers are. And also with writing things up formally too, like it takes practice. So I welcome you to like practice in any way, the shape or form that helps you. So use the Piazza board to say, here's a cool problem, let me describe it, right? And just practice sharing, describing problems and solutions with each other. Okay, so how are we there yet? Is the question.
Sorry, could you go back and explain this whole part here that you just wrote an arrow at saying scratch work? I don't understand how we got most of it, any of it.
For this A, f of n over b is less than c times f of n?
Yeah.
Okay, so what I did so I said that this is what I want to prove, right? The A is strictly less than n over b, yeah. So this is what I wanted to prove. And what I did was I whittled away on both sides of the equation, okay? So the second line here, I just plugged in, I plug in A and B because I know those are values that came to me, right? And so that second line shouldn't be surprising for you.
Yeah.
And then this third line here, right? Now I'm breaking slightly from my structure of it, that I'm kind of working on the left-hand side and I'm working on the right-hand side, and I want to get to something such that I can clearly say that the left-hand side is less than or equal to the right-hand side. Okay. There's an inequality I can use, and that came from my asymptotics. Okay. So that was up on the above. The definitions. So now I'm using all colors. It's probably going to look crazy if you go back and look at it. But this is from asymptotics. Right? If f of n is theta of 2 to the n, then I know that I can define that there exists an n0 d prime such that for all n bigger than or equal to n0, this inequality holds. This box within a box now. Okay, so now I have that inequality to work with, right? So now I'm using the inequalities from definition of theta. So I know that f of n over 2, oh wait, I should make sure that I just got really quick to do something. Okay. I need to update my C, I think. Yeah, so my n over 2, d prime times n over 2. Okay, so I know that's where these, let's see, I'll make it yellow too, that these two inequalities came. Okay, and remember, I haven't quite defined C yet. Right, and actually, as I'm seeing this, I know I need to fix it. So, right. So now I have d prime times 2 to the n over 2, and I'm comparing this to C times d 2 to the n. Okay. Now, if I say that C is equal to d prime, I'm gonna just erase what I had here. So if I have d prime 2 to the n over 2, d prime d 2 to the n, and this was by, and I'll put this in that purple color, set C is equal to D, right? Because if you remember, here we get to define whatever the C is. So when I start it, you can either, sometimes you can take a guess and you get it right away. Sometimes you just kind of need to work with it and to see, okay, I know this is a constant. I don't know what it is quite yet, but I'll figure out how to define it, right? And this is why it's scratch work, right?
Sorry, here, are we setting C equal to D or to D prime?
D prime, sorry. Yeah. And then I have, and then, yeah, okay, so then we're good. Because then I have D prime, and I know that D prime is less than D prime times D. And I have 2 to the n over 2, and I know that's less than that. So I know that this is strictly less than. Okay. So then I've whittled down my inequality to something that's true, and I know that this is true, right? So now I need to kind of step back and put it all together. And the way I do that is I walk through it kind of this way, like this U shape. I don't know how to draw this so it doesn't look too messy. I'll say take a U-turn to show formally. Okay. And then, all right, so if I had let C equal to D prime, then actually for all n bigger than or equal to n0, right? This is the part here, sufficiently large n. What I mean by that is there exists an n0 such that A times f of n over b is strictly less than C f of n for all n bigger than or equal to n0. Okay. Yeah, so then I just step through it, kind of making this U-turn. So I go from left, A times f of n over b, which is equal to f of n over 2, which I know is strictly less than d prime times 2 to the n, which is, now I can make that a strict less than d prime times d to 2 to the n, and I forgot the n over 2 here, right? Which is equal to C times d of n over d to 2 to the n. This is tongue twister for me here, which is less than or equal to C times f of n. And we had I think it shouldn't have been A equals, it should have been A times. Right, so then I've shown that A f of n over b less than or equal to, or is strictly less than C times f of n. Okay. Yeah. Okay. So now I can conclude. Okay, and how do I conclude? I know that T of n is theta of f of n. T of n is theta of f of n, which is theta of 2 to the n. Okay, so now we're done here. Super. Yeah, and the Master's theorem case 3 is kind of the most technical to apply, just because it has both those conditions. Case 2 is the easiest, just because you don't need to worry about those epsilons and such. And then case 1 is, of course, in between, because you don't need the step 2 of what you just went through. But yeah, I think also as you're working on proving things and stuff, try not to worry about the structure of it. Try to figure out how do we get to the answer, and then go back later and think, okay, how do I now write this nicely? It's kind of like a two-step process. So the next, okay, so we have other questions on Master theorem. Okay. Now what I want to do, let me see what the time is. So yeah, perfect. We're going to look at splittable. So there's the function I put up there. So maybe I can just move it. Okay. So for that splittable function, I'll put it into the prompts. What this does is, well, this is strange. I'm going to move it right there. But what it does is it takes as input an array, A from 1 to n. So we'll say that the array, it's an array of strings. And suppose I love CS. Okay, so this is what my array is, right? And the question is this splittable into words? And we'll just pretend that CS is a word right now. Okay, and then we have this, we'll say this oracle for right now is word, that maybe you look it up in a dictionary, and that you can check to see if something's a word if you hand it a subarray, okay? So I want you to walk through this example, okay? So this is also a really nice thing to do, is every time I encounter a new algorithm, always play with a small example, right? How does this work, right? And then once you walk through a small example, we can question show it terminates using a decrementing function, which means I need to define this for you now. And then if you get through that, the third part will be to what is the actual runtime. just because different groups are going to work at different paces. And why is this Miro board not loading on my computer so I can move things around? Okay, so I'm going to just scroll down here and then I'll fix. Oh, see. So thank you, whoever updated the size of that board. So decrementing functions. Okay, so what I need, and so this is used in recursion and loops, specifically while loops more often than for loops, but okay. What we need is we start with a well-ordered set. So let S be a well-ordered set. Okay, and often S is going to be our natural numbers, which will be set 1, 2, 3, 4. Okay. And actually, let's just say that zeros are our natural numbers. Some people define it with it, some people define it without. It's probably easier if we have it in there. Okay, so, and by well-ordered, I'll put here a definition of well-ordered. A set is well-ordered if every subset contains its minimal element. The infimum. Okay, so otherwise mathematically, if inf of S is contained in S. An example, natural numbers, not an example, real numbers, because the open interval, the infimum of an open interval is 0. So if the interval from 0 to 1 is 0, but that's not in the open interval from 0 to 1. Okay. So I'll say that, but I'm not going to write down that to avoid confusion. Okay. Then in recursion, we need a function call it F which goes from the state space to S. And now maybe I make these S's kind of fancy, such that X and Y are in my state space, and X is the top of a recursive call. Y is the top of a recursive call. Happening after X. Then F of X, F of Y. So Y is happening after X. It's a decrementing function. It's strictly greater than. So strict. Okay. Right. So we can think about it as if for the decrementing function, we always want maybe the size of our input, right? So if the size of our input's always getting smaller, as long as our size of our input's finite, right, then we'll reach the bottom where we have a minimal input, right? So let's go into our groups and answer these couple questions. Do we have any broad questions about what this is splittable is doing?
I have a question.
Yeah.
What's it doing?
Okay, so it's taking a word, so a string. So here I have A is I love CS, and then it's checking if I can split it into words. Okay, how it's doing that, right? And so this is splittable. This one here, this is yes, because I can split it into.
Oh, there's a function up there. I didn't see that.
Yeah, I love. And I said CS, we'll pretend that's a word. So your dictionary believes it's a word. You can also try what happens here when I do X, Y, Z. Not a word. Okay. So try those two inputs and see how is it doing this? Okay. But it should, for the first A, we'll just put them A1 and A2. For A1, it should return, we're having it return true. And for A2, it should return false because you can't split it into words. Okay. So I will put you in breakout groups. And yeah, we'll see you in the groups.
Hello.
Hello. Yeah, sounds good.
Do you want to just do the last one there?
Yes, although I'm struggling to change the name for some reason.
I think that's because I have
Oh.
the box highlighted.
Cool, go for it.
It's a bummer you can't really type at the same time in the same text box.
Oh, sweet.
Okay, cool.
So should we start with just walking through it?
Sure.
I don't have the greatest penmanship, but I can do it if we want, or if somebody wants to do it, do the actual writing.
No, you got it.
All right. All right, so let's just run through. N is not equal to 0. So we're going to do for 1 to n. So I equals 1. We'll do if 1 to, I wonder if it's 0 indexed or 1 indexed. I guess it's 1 to n, so it is 1 index. So that's great. That's really good. So basically, is the whole thing a word, or from 1 to 1? So is I a word? I is a word. So I'm just kind of making notes as I go so that I remember where I am. So then we're inside that if statement, and then we have to see if 1 plus 1, so 2 to n. So basically now we look at this section. So for that call, then it's recursive. So then we look at I equals 1 again is this. So basically is L a word, L is not a word. And then I equals 2, LO is not a word. And then so on. So then we determine LOVE is word. So then we run the function on just CS. And then eventually I think we'll find that CS is word. So then we'll run the function on just this empty string here. At that point, n will be 0. So then you'll return true. And then you'll go up the recursive call, and eventually it will all return true. So that's how it works. It's actually easier than I thought it was, but yeah. I don't know if that made any sense or if that was the ramblings of a madman at 9 a.m., but
I'm wondering how it'll handle stuff like running, right? Like stuff where words are substrings.
yeah,
Other
I
words.
think it'll totally not work.
Well, I'm not so sure though, because that for loop looks like it might save us, right? Like it'll identify run as a word, and then it will continue on and find out that it's not a word. Then it goes back to the original call and keeps iterating.
But does it keep iterating? Because I think eventually you hit return true and that kills it, right?
Well, so my thought was that, right, if we send in running, right, it's going to identify run, and then it's going to look at ning, which is not a word. So it's going to return false on ning, right?
Yeah.
And then I think it will, like it'll return false, and then it will iterate the for loop, right?
Yeah. So then, but I think then what you'll get into is your call for is splittable, like the nested if splittable, that'll return false.
Yes.
So then
Which is okay, right?
Yeah, but then eventually, I don't know. Should we? I mean, we could just walk through running. I'm curious, but I don't know if it necessarily has a bearing on our runtime discussion, but or the termination. But I am curious. So I don't know. What do you guys want to do?
Either way, if I mean, if it doesn't apply to the next question, maybe we just keep going so that we get time to talk about it. But it's okay either way.
Yeah, I don't know. Let's try the decrementing function. maybe, because I think that's the hard part. And that's the big part, I think.
Mhm.
Because I just did the easy one. that first part, walking through it's really easy.
So state space. So I guess, right, I'm thinking about, so she talked about like X and Y, right? When she's talking about a decrementing function. And, oh, wait, never mind, because Y, we're like supposing that Y is a recursive call after X. So it has to be further down the tree. I was like wondering if it could be in a different branch and how that would work, but I think that could not happen because of our assumptions.
I guess what I'm confused about is so X and Y are supposed to be in the in the state space. I guess what is the state? I guess that's kind of where I'm confused, is even backing up to that far. Like, what is the state space and kind of how does it, like, is the state space just an array, like a string in our case? Like an input?
You mentioned the length of input is like a common state space, which would seem to apply here,
Yeah.
right? Because we're like, we have a length thing, and then in that for loop, we're like iterating over it, right? It gets one smaller every time we go through the for loop. And I don't know if we can get that into the decrementing function.
Yeah, it's like X is N because that's our input, and Y is like N minus 1 or something because it decreases our, since it decreases our state space by 1 every time we loop, or potentially more. I mean, if you think of every time we do a recursive call, it's potentially even more than just 1, right? It's however many we checked.
Mm-hmm. Yes, that's true. Yeah, the state. So let me know what you guys think of this. The state space like is the array, right? And then we map it to S, the natural numbers, and like the map is like take the length of the array.
That's kind of what I had been thinking. But
then, yeah.
No, sorry, go ahead.
I was saying, and then that intuitively makes sense to me. So.
And then I guess what we would need to show is that, right, so we have some recursive call, the top of a recursive call. And then I guess we would say like define the top of a recursive call after X to be like, right, something further down the tree. And we need to show that the length of the array is smaller, which we've kind of like informally mentioned, I think.
Mm-hmm.
Yeah.
Is that always going to be true though with different, like that's true of A1 or example, but is that always going to be true? Like that f of X is greater than f of Y?
I mean, if you never do, so like in A2, that example she gave us on using like XYZ, you never do a recursive call there because you never have a word. So you just go through the loop and then end, return false.
Yeah.
So in that way, the recursion isn't what's making it terminate, it's that loop. So it's almost like there's two parts. There's almost like the recursion is making sure that every time we do a recursive call, it is shrinking our state, but the loop is also shrinking it. But I have no idea how to formally talk about that. But
Well, it feels to me, it feels like the loop is the thing shrinking the state. Like the recursive call just happens to be made on a smaller state, right?
Mhm.
that's a good point.
You like, just to make sure I understood, you were saying that you wanted our function f to be the like word length. Or did I mishear you?
I think, well, the array length, right? So there could be multiple words. Like,
Okay.
I don't know. I think that we can just assume that we'll at least have one recursive call since Y says it's the top of recursive call happening after X. Like we can reasonably, like in a case like XYZ, we'll never get into this situation.
yeah, so it's vacuously true.
Yeah. I mean, honestly, I don't think it's a good proof because like obviously that case is a real case that could happen, but for looking at like recursion like this, you had to assume that recursion happens at some point, I think. I don't know.
Well, no, I think so. Right. By vacuously true, I mean that like if something never happens, right, it's like false implies true is
Yeah.
true on our truth table. So I think like the case that you brought up where there's like no words in it, right, there's no opportunity for like the implication to be wrong. Does that make sense?
Yeah, I think so. But then how do we show that terminates?
Well,
Brittany,
so
are we totally on the wrong track here? Are we just talking about things that don't matter?
I'm trying to catch up to where you are, so maybe you will summarize what's going on.
I think just briefly, since there's kind of two control mechanisms in the algorithm, like there's the loop and there's the recursion. And so the loop is kind of the thing that's shrinking the sample space a little, like, and then the recursion is like directed by where the loop tells it to kind of go. So we're not sure really what we're debating is like, if in that case, XYZ is word will never be triggered. So it'll just go through the for loop and then return false. So how do we talk about termination if there's never recursion like triggered?
Yeah. So the termination, it doesn't have to do with the input per se. It has to do with, yeah. And I forgot we have both in here. So,
because we were thinking about making our f of.
To make sure it ends. Yeah. Go ahead.
Sorry, I was saying we were thinking of making f like the array input length, so n, essentially, and then each recursive call, the n will be smaller. Is kind of what we were thinking. Is that kind of on the right track?
So that's the decrementing function for the recursion. Yeah.
So is that enough for this algorithm, I guess, is maybe the question? Or do we need more to deal with that loop?
Yeah, for this loop, actually, since it goes for I equals 1 to n, we know that the loop happens exactly n times. So where we would really need a decrementing function to prove termination would be if it said while I is greater than 0, right? And then wild things happen with I in the middle and, multiply by 2, right? Or something, then we're never going to get something negative or so.
Gotcha. Yeah, it sounds basically exactly what Nathan told me. So he was right all along. Anyway, cool.
Yeah. Super. All right. Well, I'll hop into another group to see how people are doing, but you guys seem pretty good. Oh,
All right. Yeah. Also, is my name on the mirror board? Does it have my last name like Brittany wants to? Okay, sweet.
So should we start with that F is mapping? I mean, really, is it F of n is equal to n?
Well, it takes in an array, right? Would be the input.
Yeah. This is the part that I always struggle with is how do you, like when we actually start formally writing it, where it's like, so our function is F of an array equals length of array. Maybe?
Yeah, I would agree with that.
Which then maps, well, I don't know if we have to show that length of array returns a natural number. I'll just put a note.
I think you can just say like F maps the array size to the natural number line with an arrow. It's kind of the formal. Does that make sense?
Yeah. Do you want to
Well,
write that or draw that or whatever?
you can try.
I think we could also just say this.
Yeah, that works too.
Oh, great. That's better. So then we can show that like each recursive call, and we can say I is greater than or equal to 1 because of our for loop. Then R is at I plus 1 to n. The idea being so length of our, I'm going to say our prime is equal to length of r minus I plus 1. So f of r is strictly less than f of r prime. What do we think? I kind of went AWOL a little bit. Nay, I don't know.
Yeah. I think it's very nitpicky, but I'm not sure about the +1 because we're not a 0 indexed array.
I just took that from the recursive call where because if we didn't have the +1, if I was 1, and remember we're 1 indexed array, we could just call the same array every single time in theory. Because it's from on the algorithm there, it's that part is what I was copying from.
Oh no, I like that +1. The +1 and the line below it.
Oh, I got you. Like that one here.
Yeah,
Let's see.
right. Because we took off the 1 spot, the 2 spot, the 3 spot, all the way up to the ith spot.
I see what you're saying. Yep. That's super weird, and I hate that. Like you're right, but I hate that we're 1 indexed arrays because it should be. Yeah. This is why we 0 index arrays. Yep. No, you're absolutely right. But regardless, since I is at least 1, it'll always decrement. So.
Yeah, and that is the key part.
All right. If we're happy with that, should we talk about the actual runtime?
Yeah. Yeah, so I guess it wouldn't not help much if I wrote this down on paper. But I think I'm gonna do it anyway.
Yeah. I mean, just intuitively, without any proofs, do we think the runtime? To me, it looks like n. Oh, we're losing our rooms.
Oh, so yeah.
See you guys.
All right. Do we have any thoughts, questions, concerns coming out from working on these groups? If there's coming in, I'll take thoughts, questions, or concerns.
How would our algorithm be different from selection sort in terms of complexity? I can only think of it being n squared, but it's very similar to selection sort, so I'm thinking n log n.
Okay. So you're thinking it's close to selection sort.
In similarity, like. But okay, I don't know.
So you're guessing that the runtime is n squared because of the similarity with selection sort.
Well, selection sort is n log n.
Oh.
I believe. Anyway.
Well, okay, we'll discuss in a minute. But okay, does this fit into master theorem? Did any of the groups have what the worst case recurrence relation is?
It's 16, just so you know.
Okay. Yeah. So yeah, okay. Yeah, so it doesn't fit in master theorem. So you kind of working through the examples, hopefully help build the intuition. But the recursion tree will give you a guess as to what this runtime is, right? And I'll see you all next week, and I'll look forward to getting all of your homeworks in. But maybe we'll talk on Piazza about what the actual runtime of this is.
Yeah, have a wonderful day.
Cool. Thanks.
Thank you.
Thank you.
Professor Spacey, can I ask a question for problem 2 on the homework tree real quick? So
I'm gonna pull it up.
recording the subtrees in that binary tree. What would be maybe the best way to go about that? Would it be like storing them in an array and then comparing those? Like, should be larger or?
Hold on.